How do modulation techniques balance signal quality and bandwidth? Imagine trying to send a message through a crowded room. You want your message to be clear but also not take up too much space. That's what modulation techniques do in signal processing and control systems. They encode information onto a carrier wave by changing its amplitude, frequency, or phase. The challenge is to make sure the signal stays strong and clear while using as little bandwidth as possible. Different modulation schemes handle this balancing act in unique ways. When you change the amplitude, frequency, or phase quickly, you need more bandwidth to keep those changes clear. To fix this, engineers use filters like raised cosine or Gaussian filters. These smooth out the transitions, reducing the bandwidth needed and cutting down interference from nearby signals. This makes the signal cleaner and easier for the receiver to pick up. Now, let's talk about how data rates and signal quality are linked. Higher-order modulation schemes like 16-quadrature amplitude modulation or 64-quadrature amplitude modulation can pack more bits into each symbol. This means you can send more data in the same amount of bandwidth. But there's a catch. These schemes are more sensitive to noise and distortion, so the signal can become less reliable if the channel isn't good. On the other hand, lower-order schemes like binary phase shift keying or quadrature phase shift keying use more bandwidth per bit but are more resistant to noise. They keep the signal clearer, especially when conditions aren't perfect. Adaptive modulation takes this a step further. It adjusts the modulation scheme based on the current channel quality. If the signal-to-noise ratio is high, it switches to a higher-order scheme to send data faster. If the channel gets noisy, it switches to a more robust, lower-order scheme to keep the signal reliable. This way, the system balances speed and quality dynamically. Constant envelope modulation techniques like Gaussian minimum shift keying keep the amplitude steady. This allows power amplifiers to work more efficiently and linearly, which helps preserve signal quality without needing extra bandwidth. Filtering and pulse shaping also play a role. They reduce sudden changes in the signal, narrowing the bandwidth. But they must be carefully managed to avoid distortion that could harm the signal. Power amplifiers need to boost the signal without adding distortion. Technologies like digital predistortion and envelope tracking help keep the signal clean and efficient. This is especially important in high-speed networks like optical communications, where high data rates are essential. For example, in optical fiber systems, combining higher-order modulation with error correction allows transmitting hundreds of gigabits per second within existing channel spacings, balancing bandwidth use and signal integrity. In essence, modulation techniques find the best middle ground by choosing the right scheme, applying filtering, and using advanced amplifier technologies. This balance ensures signals stay strong and clear while making the most of the available bandwidth. It's a careful dance that keeps our digital world running smoothly, whether in wireless, wired, or optical systems.